Hello and welcome to lecture 7. So as you see from the title, it's about decoupling. More generally, the lecture this week are kind of shifting gears. So remember in week 1, we introduced the course, we introduced Chisel in a very superficial sense, talked about combinational logic. Then week 2, we ramped up, we talked about sequential logic in Chisel, and at that point we knew enough Chisel to do whatever you could do in structural Verilog, and then we kind of added on more Scala to add more structure and started building up things look more like generators, right? Things like those chip registers, right? The ley lines where we had an arbitrary number of registers and we compared instantiating that with a for loop with var as opposed to with recursion. Today, and more generally this week, we're talking about building up more abstractions in hardware. So these are abstractions that will allow us to make our designs more sophisticated. In this case of today, talk about the coupling. That is, we have two interacting components. How do we make them interact in a way where they aren't so tightly bound that they're always holding each other up? Okay, so in order to talk about it today, we'll talk about a few things. We'll talk about the coupling, but before we do that, we'll talk about something called Scala case classes as a way to better encapsulate the parameters. Then we'll talk about the Chisel queue, which in this lecture we'll see how to use it. In a later lecture, we'll actually go about building our own queue, and we'll kind of see this come back a lot this quarter. Okay, so what is the goal here? The goal is when you have a substantially large design, you're going to have more and more components. You want to decouple them. You want them to have some amount of flexibility to operate independently. As things get sufficiently big, sufficiently complicated, they need to be decoupled, right? So what do we mean by decoupled in this course? We mean some sort of connection with time sensitivity. So not only does that mean it's not combinational with some sort of, registers on both ends, so it has some amount of uh, flexibility there. We also mean that, it doesn't happen every cycle. It can happen cycles only when both sides are ready. And so when the coupling is done correctly, it can really simplify your design. You can build a bunch of components that are decoupled, put them all together, they all understand decoupled, and they all fit together great. And they're much more reusable, right? The alternative would be components that are very specialized to operate with each other, and then we try and interoperate them with something else. They aren't quite as compatible. So the coupling done well really improves reusability, and that's, of course, one of the key parts of this course is how do we make things very, very reusable. Um, cool. Okay, let's actually see some concrete stuff. So as always, let's load up a notebook. Uh, Good to go. Okay, so before we dive into coupling, as I said before, I want to cover something called Scala case classes. So you're starting to see a little bit of that depth of Scala here, where Scala, when it advertises itself, talks about it being Java with a lot of object-oriented and functional programming features. Java, of course, is object-oriented, but why would they repeat that with Scala? Well, they had a lot of new additional object-oriented features. That's why. So we've already covered class and object. Today we're covering something called case class. So what is that? It's a special kind of class that makes a lot of common cases really simple and easy to do. And for that simplicity and that utility, we actually lose some functionality. But that's okay because we're not going to need that, right? So a lot of times we just kind of want something like a struct to kind of just toss together a few fields and maybe even add a method to it, right? So let's say we have a case class about movies. We have a name for the name movie and of course the year and maybe another string for its genre, right? Um, and let's say someone wants to, say what decade the movie's from. Well, we'll just, uh, you know, say the decade. Sure. So um, if we go ahead and fire up this code, maybe I'll just leave this portion uncommented right now. Uh, sure, we can go ahead and define this case class. We can instantiate an instance of it. I'll point out right away that notice how when we instantiate M1, that appears in the log, no problem. But there's already a string printout of it, right? Um, and that string printout is something that the case class gives us automatically. So if you have an arbitrary Scala class and you try to print it, you're going to get some sort of, ugly thing like we've seen before, where it's just going to be the location. I think I might be able to get that happen if I comment that out. We can comment this out too. Yeah. Oh, you know what? It's still remembering as a case class. Why don't I call this movie too? There we go. Ooh. Why is oh? And of course, when you do normal objects, you got to say new. And yeah, so you can see normal object, have to say new and etc. But as a case class, life was a lot easier. It handles new for us. Lightning companion object exists. And I've crashed my Scala kernel. Don't worry, we can uh, restart all that um, and bring this all back in. But yeah, so key point about case classes, right, is that we are now able to have this kind of convenient thing to pull us together, right? So now hopefully it should all work. Oh, thank you. This is why we're a team. Thank you so much. Forgot the case was a good comment from the audience. Okay, good to go. So a lot of things are already available, right? So now we can just declare a case class, use it, grab the fields, don't need label and val, go ahead and declare another case class, no problem. Now, it's also kind of fun is that as case class, I have a method called copy, right? So I'm allowed to say, hey, uh, make me a new case class. We're keeping everything the same. I'm just telling the one field I want to change. I want to change the year. Yeah, you got that, right? So guess what? There's two movies called The Avengers. You look at IMDb. Um, and then, of course, you can call the functions on it. Great. So these are all there. We'll use case classes quite a bit in this course, right? What they're useful for is for just kind of encapsulating what your parameters together, right? Imagine if your generator, maybe if it has one or two parameters, you can just have those as individual fields. We start having, dozens of parameters. You should put them in case classes, right? Or even case classes nested inside of each other. Um, Not today, but in a future lecture, we'll show something called pattern matching. And it once again shows another benefit of case classes where we can kind of really easily get things into and out of them. Okay, so as promised, let's see how we use them for a parameter. Remember from prior lectures, we've talked about building this counter we kind of keep spiffing up. And rather than having a bunch of fields, we're going to have a case class here. So we define this as counter params. And actually we have yet another field start, which we set by default to 0. We, of course, can override that. We're also going to encapsulate that logic we have to figure out the width of the field inside the case class, right? So that makes the generator simpler. The generator just knows, hey, I need to ask this case class, what width to use. The case class is going to figure that out. It's also great to put this in the case class because that way it's a single source of truth, right? That way this is used twice but written once, right? So that way there's no notion of these being out of sync or anything. We, of course, also can use a start for resetting. This all kind of comes together. So you see this case class makes this not just cleaner code, but much more, robust and flexible code. And yeah, like always, we can print the Verilog out. You've all seen this Verilog. We can show off today, oh yeah, let's say we want to have it start at 4. Yeah, no problem. If we scroll down in there, sometimes I have to double click on this. Oops. There we go. I can scroll better. We can see there it is resetting the 4. Cool. Questions so far? Yes. Yeah, so what does this not start? So our counters so far have had this assumption that, the count should start at 0 and go 0, 1, 2, etc. And we're making this more flexible and saying, you know what, we can start at some arbitrary number. So maybe not 0, maybe start at 2 or something. Is it just, low hanging fruit in terms of adding flexibility to our generator? It's another parameter, chuck it in there, tweak it, and do that. And so most users probably don't care about that. So guess what? We can leave that off, and the default of 0 is going to be used, and they're happy and they're all good. Like I said, it's kind of one of the things that kind of see as you build these generators, of adding that flexibility to make it more reusable is kind of a key thing, but we don't want to fully expose too much complexity, right? Someone doesn't care about when it starts, they shouldn't have to worry about that. Great. Okay, let's keep going. So, um, now getting to the main meat of decoupling. So there's something called a handshaking protocol, which is you have two entities. Let's say I'll call them producer and consumer. So one person's creating things, one thing's consuming things. If there's a bi-directional relationship, we'll think of that as, let's say there's two things that both are producing and consuming. We'll think of that as two producers and two consumers, going both ways. But for now, let's focus on one direction from the producer to the consumer, right? And like I said, both sides are sequential components, where both sides have internal state. This is a non-combinational path between them, but how do we decide when it's okay to exchange data, right? And the producer could always produce data, but the consumer's not ready for it. That data is not going to be accepted. So how do we have some sort of way to dictate when both sides are ready? When the producer's willing to send and the consumer's ready to accept that, how do we kind of declare that? That's what your handshaking protocol is. So we're going to cover a particular protocol in the next slide. But before that, I want to kind of set the stage. So more generally throughout computing and engineering, you're going to see this trade-off. It's a recurring trade-off, right? This notion of when you do things centralized versus when you do things distributed. And they both have demerits. That's why we're talking about both of them, right? You don't always do only one of them. There's a time for each one, right? So what's the advantages for each? Centralized, when it works well, it's simple, right? Everything is all centralized, right? You can see all the things. So in other words, you have n entities, you know the state of those n entities, and you have that all information in one location. You can make decisions very easily and kind of spread it around, right? What's the challenge? Well, the challenge that number of entities you're controlling is five things. Sure, you may bring information from five things to one location to make decisions. If you have a million things, bringing information from a million things in one location is not going to work, right? So that's why you have distributed or peer-to-peer, where you have components that can kind of operate semi-autonomously, and that's great. However, of course, the trade-off of distributed is because you're peer-to-peer, you have to make decisions knowing you're not the only one making decisions, and you have to make decisions with partial information. So that's just trade-off, right? So in a number of scenarios, computing, engineering more generally, kind of the outcome is, well, you know what, for a certain system scale and smaller, you're better off centralized. And for a certain scale beyond, you're better off distributed. And what's interesting is even if you have a distributed system, it can be a distributed system of components that are internally centralized, right? And so that's what the conversation is. Okay, at what scale I switch from centralized to distributed? So you're kind of starting off centralized, you get sufficiently big, you become distributed. Inside those components, they may still be internally centralized. And that's usually when we build hardware. Your module has always internal components, understands those are all centralized. But between modules in a sufficiently big system, it could be distributed and thus decoupled, right? So now coming back to our data transfer conversation, what do we need to be able to handle? We need to be able to handle the notion that the producer is not always sending data. They need a way to say, hey, you know what? I have nothing to share with you right now. You can hang out, you can chill. And at the same time, the consumers will also say, you know what? I can't take anything right now. I'm, too busy and able to push back. We call that back pressure. I say, I can't take anything more. So these are the kinds of things we want to have in our protocol. The ability for the producer to indicate there's no data to be sent, and for the consumer to be able to indicate that they can't receive anything, able to apply back pressure. Okay, so the protocol we're using, I'm hopefully seeing in other hardware courses, it's called a ready valid protocol. And there's a lot of things that are really similar, so please pay attention to the details, right? And that is, we're going to have these two one-bit signals that do the handshaking, right? So valid is sent from the producer to the consumer. And it said, when this is true, it is saying, hey, I'm ready to send data. Meanwhile, on the consumer, you have a ready signal, which is true when the consumer is ready to receive. The actual data is sent on the bits, which could be 1 bit wide. It could be, an entire bus of 100 bits. Now, the key thing to point out is just because you're ready to send data doesn't mean data is actually sent, right? It only is sent when you are both ready to send data as a producer and the consumer is ready to receive data, right? So you use both valid and ready at the same time. So here we have a little waveform. You can see, clock cycles, okay. So these decisions are evaluated on the rising edge of the clock. And sure, there's a rising edge of the clock here where valid is true. So, maybe there's data to be sent. There is data to be sent, but it's not ready to be received. Ready is false, so no data is sent. So the actual bits are still or valid they were originally. And then, of course, next cycle later, we really evaluate. So wait, both ready and valid are true. We call this firing. The couple handshake happens. And now we can send the data. And then the producer is, wait, I have now sent D0 to the consumer. I can now get ready. Next thing I want to send, which happens to be D1, for example, right? And you can see it sends D1. Next cycle later, ready and valid both true at the same time. So we send D1. Then the producer says, you know what? I have no more data to send. And so it deasserts, turns off valid to 0. At that point, the contents of bits does not matter because we aren't doing any exchanges, right? So the data here does not matter. So here's the high-level protocol. I see you've probably seen this maybe in a digital design course. The reason why I was very careful to kind of go up to the semantics is there's subtle nuances about, what is always true versus always false between different versions of this. Questions? Okay, let's go ahead and try and use some hardware. Um, so Chisel, in the spirit of making things easier, built this into the standard library, right? So this ready valid signaling is an extremely common design pattern. And so let's just add some language constructs to make this easier to use, right? And so rather than writing your own ready valid stuff, you should use the stuff for ready valid inside the standard library. Number one, of course, there's less code for you to write. That's great. But also by reusing other people's code to hopefully correct, less chance of you to make a mistake. And also by being more standardized, it improves readability for someone else. So someone else who's not read your project but has read Chisel code gets up to speed more quickly, right? That's a good thing to have. Um, and so what do we do? Well, basically, you take a port that you want to send data on, and then you annotate it with what kind of protocol you want, and then Chisel will automatically add in the additional wires you need to make that the case. So, for example, if I want a decoupled, I want to have both ready and valid. Um, I take that data port and I wrap it in this decoupled construct. It turns out maybe you want only what's called valid in Chisel, meaning you want to indicate if there is or is not little valid data on here. So that's the producer side. There's no ability to have backpressure from the consumer, right? So there's no ready signal, right? So it's just valid. In other words, I can mark if the output is good or not good. The consumer is, obliged to take it, right? Versus in decoupled, data is only sent when the producer has something to send, i.e., valid, and the consumer is ready to take it, i.e., ready. Um, and so there's situations for both. Um, I kind of like to think of valid, kind of like that Scala option we saw earlier. Remember we saw Scala option where it has this notion where we have a value, and either there's a value and a number is given to you, or you can note the notion that there's nothing there. And the same thing is kind of true taking a port in your module and marking it as valid. You can basically say, hey, guess what? This thing, either valid is true, take a data, if valid is not true, don't even look at data because it's just not even something there. Um, Questions so far? So then one last little wrinkle, if you're an experienced digital designer, you may run into this. There's something called a combinational loop. That means that inadvertently, there is a path in your design where you can feed back on itself without going through any registers. So it's typically a mistake. Usually as a human, of course, you try hard to avoid that. Sometimes with ready valid signaling, you can do that inadvertently. So it's not anything unique to Chisel. This is just a general issue of ready valid stop signaling. Um, if the generation of the ready signal or generation of the valid signal is completely independent of the other one, you are safe. However, some people have a design where they say, you know what? Let's say I'm a consumer. I'm only going to turn valid on if ready is on, and somehow that comes to that logic. Then you've made a mistake. Then you've put yourself in harm's way. So I said, make sure that ready and valid inside your endpoints, if those are completely separate, then you're okay. But if they have a path between them, if there's a path to go from ready to valid or vice versa, that's where you can have a combination loop. And it can be really sneaky because what will happen is you'll be doing your design, you'll do it on one side, either producer or the consumer. Do it only on one side gives you a U shape, right? So it's not quite a full cycle yet. You only have a U. It's this lurking latent problem in your design. Then all of a sudden you change something else and you end up inadvertently connect the other side and you get a cycle and you have a loop. And yeah, you may have had to start looking at both sides. So whenever possible, try to derive the logic from ready and valid from things that don't depend on the inputs, but easier said than done. Okay, so I just talked a lot about combination loops. Let's see what they actually would look like, right? As I said, they are a uncontrolled feedback path where you don't go register, right? Um, and so here's an example of an adder where the output of the adder goes and feeds right back into the adder. So electrically, this is not good. This is not going to do good things. And so you may hear the term when referring to registers and clocks as the word synchronization, right? And that's actually the way to think of them is they're actually a form of having these state changes all happen at the same time, rather than having the value.wire change haphazardly. Imagine this, originally somehow magically imagine this wire was zero over here, so 0 plus 1 is 1. then it's 1, feeding in 1 plus 1 is 2. In theory, that might something that might seem to work. Remember, eventually this is going to not work well, right? There's going to be multiple wires for multi-bit signal. They're going to eventually get out of sync. There's all these different logic gates. It's going to be reaching some very weird unstable state. And so um, you basically just about never want a combinational loop, especially not in a chisel style design. So to show you what happens, let's do that. So here I've written the counter, like it's basically shown on the right, and I pass it to the chisel compiler. What does it tell me? It tells me it was a combinational loop. So it detected that, you know what? You're not going to be happy about this. Now, looking at the output, it may not be hyper obvious what's going on. So let's talk about it, right? So number one, there is this module loopy counter, and it recognizes, you know what? IO count, it's kind of tracing through it. Goes into IO count underscore T, underscore T1, and then IO count. So remember from prior conversations, these leading underscores indicate internal unnamed signals. But basically, it says there's a way to go from IO count back to IO count, right? And we can see that, right? Basically, um, IO count comes in, adds 1, and the amount is assigned back to IO count. So the solution, of course, is to put a register inside here. So this is unlike the picture. We do that, no problem. This is perfectly valid counter. There's a register in there. We're happy. So like I said, so combination of loops, look them up a few times. They're a mistake. Um, there are some really extreme cases where you not just are okay with combination loop, but you intentionally make combination loop because you you know uh, you know it's going to converge. So you may have heard something called clockless logic, where basically they can build these gates with no clocks, and these gates are basically all combinational races and combinational loops, but they're designed with a logic function such that they converge. And so people write these in Verilog, and they watch a Verilog tool spit out tens of thousands of combinational loop warnings, but it somehow proves is the correct design in the end. Chisel, there's a way to turn off combinational loop warnings. You will definitely not need that in this course. You should not have combinational loops in your designs. Cool. Questions so far? Yes. Oh, so how could I get randomness? So great question. So do combination loops have some notion of randomness to them? A little, not as much as you would like. So the term that's often used is something called metastable, meaning that depending on how the circuit's set up, and it could actually depend on the exact manufactured part, a combination loop could continue to vary somewhat erratically, or worse yet, it goes into a metastable state, meaning that it is no longer changing, but it may be a thing you don't expect, right? So in this course, we talk about things always in terms of binary, 0 or 1s or logic values. Remember, in practice, these are actual voltages on wires, and based on the nature of the circuits, you actually can get trapped in this middle ground. So let's say your 0 is approximately 0 volts and your 1 is approximately 1 volts, and maybe if you go metastable, you might be at 0.6 volts and it's locked in there and it can't get pulled out. That's like really bad. Um, so hopefully you can avoid metastability. But to your point of, let's say I want some sort of randomness from a circuit, yeah, there are analog circuits people can make custom that have this notion of having some notion of randomness to them. They have definitely feedback, but they aren't quite a logic loop. They're more to say analog feedback kind of thing. Cool. Okay, so after all that and my severe warnings about how to avoid combinational loops, let's actually just write some decoupled stuff and hopefully not have any loops. Right. So first, let's just use valid. Remember, this is the one that is just kind of like a Scala option. Right? It's basically marking the fact that this output may or may not exist. And this really trivial example just really passes things through. So the input is some, W bits, and we have an enable signal, and this is just showing, what your wrapness and valid. All of a sudden now out is a bundle. We've covered out the last lecture. So as a bundle, there is now a dot valid field and a dot bits. So dot bits is the payload. So sure, we can attach that to the io.in, and the valid we can attach to enable. So from the point of view of someone looking at this module, yeah, we just kind of, tie that in through. Now if we go ahead and use this on the other end, the person receiving it, what can we do? Well, the receiver is receiving this uint. One thing I didn't cover, I'll go back a few slides to pull up. Um, so what is the native direction of these terms? Think of it from the producer going to consumer. So if you don't If you just mark it as only valid or only decoupled, it's like the producer going to consumer. So thus on the consumer side, you kind of need to mark this as flipped to get the reverse directions on the ports, right? So we see on the receiver, now we need the flipped in addition to the valid. What we're going to do is we're actually going to build this kind of not buildable, but simulatable circuit where when we see the input is valid, we'll go ahead and label that as such. And then in our test bench down here, it's going to simply, run for 8 cycles. So here we are using a for loop we covered this before, the range notation, sure. And we'll step through each cycle. And then what we're going to do, we're going to take a cycle number and actually poke it in as the in bits on this, dot in. For our own curiosity, we'll print the cycle number, sure. And then here's a little bit of cleverness in the test bench. For that valid signal, we'll set that true only on when the cycle count is even. So after all that, what happens? Well, you can see, yeah, we ran in cycles, cycle 0, 1, 2, etc. And you can see on the receiving end, we only printed received when I was valid. And of course, I was only valid when we have an even cycle, right? So this is an example of Gus kind of use. This is a very minimal example to kind of show the syntax working, but hopefully it kind of makes sense. So you can imagine, now as a receiver, you can now appreciate there's input coming into you that may or may not be valid every cycle. Cool. Questions so far? Okay, let's keep going. So what about decoupled, right? So valid is only one way. Decoupled has the two directional signaling, right? We have the notion of I'm sending valid data and the receiver is ready to receive, right? So like before, to make something decoupled, we just wrap that port in its decoupled term. And then what happens? Well, so what we're going to do is we're making a counter. This counter is a little special. What it's going to do is rather than just counting when its enable is true, we're going to count when our enable is true and the consumer of this count says they're ready. So you can see this, advanced counter field is true when not only is my input enable true, but also ready. So this may not be obvious, right? So io.out, of course, is this field. The coupled adds in some new wires, right? Adds in ready and valid. So now I have a dot ready. Even though the dot valid is an output from this module, dot ready is an input coming in, which is why I can use it over here. Right here I am now using the chill standard library counter. So I have kind of the enable signal, which we just labeled right there. We're also going to take a maximum value, sure, as a parameter, no problem. The actual count bits, sure, we can attach that to what comes out of the counter. And then the valid will just pass as through from enable. As an additional bit of syntax, you may remember from last time I talked about things like chill standard libraries counter, which is technically an object rather than a module. And you can return, a tuple. Sure, but that's a detail. Code it up, nothing too wild down here, but just notice how, like I said, we wrote the coupled and we get, dot ready, dot valid, and dot bits, right? They're all kind of automatically put in there for us. This is something that, should be done carefully and judiciously, where on the one hand, wow, isn't that nice? I have all these fields for me. I don't need to, manually write 3 lines here, right? Out underscore ready, out underscore valid, out underscore bits. On the same time, if you're reading this code for the first time, you're like, where the heck did dot ready come from, right? And so hopefully it's not a surprise because we're talking about the couples. This is a kind of a interesting software engineering trade-off where when you really encapsulate things with object-oriented programming, you can make your line count really get reduced, and that's nice. But sometimes things kind of poke through. In this case, the fact that out has a ready and a valid is now visible beyond this. That could be a leakage of complexity, right? And so in this case, we argue it's okay because the coupled is such a widely used child feature. Hopefully everybody understands what that's for. But when it comes to your own module, sometimes if you can't fully encapsulate something, maybe it's better to non-encapsulate it. That way it's always visible from the beginning. Okay, questions? Let's build oh yes, go ahead. The counter does what? Yeah, good question. So who's waiting where? I'm repeating this for the recording. Um, so this counter code from the chisel snare library, yes, it has an enable signal, which is this first argument. That enable signal, if it's true, the counter counts. If it's not true, it does not count. And so we are adding additional logic onto that enable signal, basically that there's enable coming from us outside of us, as well as the consumer of our thing is ready. That's kind of thing. So we're adding this additional logic to the enable. So yes, so the pausing is occurring inside the counter. You're right. When it's got turned into the Verilog, that wasn't obvious. Like, where did that come from? Well, you can see, right? Advanced counter was this wire made internally, and then it found its way inside the if statement here. So if advanced counter was not true, we actually didn't change the count. Good questions. Okay. Um, so beyond just adding these other wires in, things like .ready, .valid, these features in Chisel, decoupled and valid, also actually add in some functions. And so we've already seen that before, where we can make functions that kind of structure our generators and our designs. Now, I want to be really clear, these functions um, aren't so much functions execute in hardware when it's running. They're just kind of some shorthand we can use when we're writing our generators, right? There's some very common scenarios. For example, fire, right? Fire is when ready and valid are true at the same time, right? That's when something actually gets sent on this particular protocol. Let's say I want to send something, right? If I want to send something, I both need to change the bits to the new value and set valid to true, right? So that's enqueue in the course data. If I don't want to send anything, I can say no enqueue and it's going to go ahead and set valid to false. If I also, of course, have the reverse things. On the receiving end, I have DQ, as in, I'm ready to take something, or no DQ if I'm not ready to take it, right? So we'll see this in practice in just a second, right? So let's try this out. So here we have our count when ready, right? So we're going to take in enable and we're going to print out like before. So it's kind of what we saw a second ago, except we're now going to use some of the signaling things we just talked about. So if you go back a few slides, yeah, we had this kind of all tucked in there, but here we are setting bits invalid, right? Alternatively, now we're going to go ahead and use the enqueue feature and actually pass in the data, or to no enqueue to mark we're not taking anything. And in the comment area below, I have equivalent chisel. You kind of see some of the benefit, right? It says, one line replacing two lines. And it's not just about saving lines, it's also more clear, right? If I'm reading this quickly, I have to kind of parse, oh yeah, this is both setting bits and valid. No way, since the same base name, so they're probably a couple things together. This makes it more clear .enqueue, right? I'm setting this data. I don't need to actually remember the fact what .valid's called. I know this is going to be decoupled, and it's going to be handling that. And likewise, of course, if we're not saying anything, we can do a no enqueue. We can, write a test bench like before. In this case, we have a maximum value counter of 3. We're going to always have the enable on, so it's always trying to count, but whether or not it counts is dependent on the consumer also being ready. And we're, in this case, deciding our consumer is going to be ready arbitrarily. We decided when it's an odd cycle number. Sure, why not? So you can see, for example, cycle 0, there was no change in the count. Cycle 1, um, still no change, but next cycle 1 is truth, enables truth, and the count from 0 to 1. You can kind of see counts every other cycle. Cool. But yeah, I mean, you can see this code is, I could just as well mix and match it, sure. But it's nice to use these helpers to kind of really get that maximum clarity, what you're doing, that maximum structure. Cool. Questions? Yes, go ahead. Correct, yeah. So the way these decoupled and valid wrappers work is, yeah, they're from the perspective of the producer. So it's the output direction we wrap as decoupled or valid. If we want the input direction, we got to use that flip command we saw before to turn it around. The reason why we don't use the word input or output is because if you use the input or output command, that makes all things in that thing go the same direction. And these interfaces actually are bidirectional, right? Even a valid interface, a valid is actually one directional, but decouple is bidirectional, right? There's ready and valid going in opposite directions. So to label all input or all output is not quite the right thing to say, but that's why we say it kind of goes in the producer direction, the direction from the producer to the consumer, and then if you want the other direction, you call it flip to go from consumer to producer. Cool. So uh, all that to have this decoupled abstraction, what can you do with it? Well, a really common design pattern is to have these large components in your design, and rather having them kind of tightly interacting, not only are they decoupled, we put a queue in there, and that queue allows them to not quite go at the exact same times, right? So, for example, we have like a 4 entry queue. So the consumer, when it's ready, can try to dequeue something. And as long as something in the queue, it has work to do, right? Whether it's one element or 4 elements, it doesn't really care. All it cares about is something for me to do. Same is also true for the producer, right? The producer, is producing things and it doesn't quite care if the consumer is ready for it right now. It just cares that there's room in the queue. So as long as there's, at least one slot available in the queue, it can put it in there. So that queue gives you some amount of decoupling. And so um, we've all experienced this in our lives and daily lives quite often. We stand in a line in some place in public. That's what you're looking at, is the fact that, the rate of arrivals and the rate of consumption aren't quite exactly the same, right? There's, some differences. And if there's fundamentally a mismatch, like the production rate is way greater than consumption rate, you're going to have a line around the block, right? We've all seen that. Or in the case of this hardware queue, the hardware queue is of finite capacity. It's going to fill up, and then it's going to say, I can't take it anymore. And so, from the point of view of the producer, these are decoupled interfaces, both NQ and DQ. It's going to see this is not ready and they can't send anymore. So, then the producer has to stop, right? But the reason why you have this queue is if you didn't have a queue and you only had a decoupled interface between producer and consumer, in order for the producer to be able to send something, the consumer needs to be ready to take something, right? And sometimes it is, sometimes it's not. By having a queue, you have the ability to kind of, put a few things in there at a time and it takes some time. Maybe if you're a little producer, takes things a while. You can imagine maybe like, let's say you're at, an airport checkpoint. Maybe a carload arrives and people get off to check in. So there's now a 4-person line going through security, but they kind of get drained one at a time. And eventually they get handled, right? So queuing is a little bit of decoupling, a little bit of ability to have these two things have different arrival rates. However, the rates are fundamentally really different throughputs. Of course, you have a problem. But queuing is somehow decoupling. It's a really common practice between large, complicated components to have, multi-cycle operations to have these queues between them. So, like a lot of other useful things, Chisel has a generated standard library for queues. We really recommend that one. However, we will be in a future lecture making our own. Okay, so what happens? We talked about this before, right? These queue interfaces, NQ and DQ, are actually just decoupled. And so on the prior session, it was a single layer, but we know decoupled actually has ready and valid as well as bits, right? So you can see all of a sudden there's freaking 6 ports on this queue, right? Something is designed to like just be some little buffering is now all of a sudden 6 ports, right? Um, Fortunately, when writing it, we only need to write, NQ decoupled, DQ decoupled, and it does the rest of it for us, right? This kind of happens a lot. You have a lot of decoupled ports in your design, and all of a sudden the actual wire count of Verilog gets really big, but from you reading Chisel, you're kind of seeing this, 1/3 as many signals because you're only seeing these as decoupled rather than all the fields individually. So using the Chisel queue, which of course you can always pull up the Chisel doc. Come on, what? There we go. Yeah, you can look at it before. You see you give it the type, it's parameterized, and a number of entries, right? So yeah, if I want 8 4-bit uints, you got it. There are some other fields in this queue that I'll talk about now and will make more sense later on. These are optional. So you can see, for example, this usage right here, I didn't bother specifying these. So what are they? There's a few different scenarios that come up in your queues. So it might actually be easier to show these on a prior slide. The first is pipe. So imagine your queue is full. So you have 4 entries. All entries have a live data in them. So the question is, is the queue ready to receive something else on the enqueue port? Your answer would probably be no, because it's full, right? That makes sense. However, with the pipe feature, if your queue is full, however, the consumer is dequeuing that cycle, you have room for one, right? Because you can put one on knowing one's be taken off that same cycle, right? So you're basically simultaneously enqueuing and dequeuing into a full queue. The net number of elements inside that queue is the same. That's okay. That's a little dicey, right? Because basically what you've done now is you now have a path from the ready signal coming out to the producer uh, that is based on the ready signal over here, right? So there's now a path going through the queue. Until that moment, these were, you can imagine like a jagged line here. These are independent wires. But now all of a sudden, if this parameter is true, there is a path here. Depending on how your entire circuit's written, this can cause a combinational loop, which is why this is a parameter you can turn on or off. But yeah, in a normal case, and you can turn this on, that's great. You can use all the entries in your queue. Otherwise, you get in a scenario where you have to have at least one free slot in the queue in order to enqueue. With pipe being true, you can enqueue into a full queue if someone's dequeuing at the same time. There's also a flow parameter, which is once again another optimization, which is if I have an empty queue, uh, that would be really annoying to kind of trying to send data from producer to consumer. The queue is empty, but the queue adds a one cycle latency, right? So kind of get written into the queue, and one cycle enqueue into the queue, and that cycle gets dequeued from the queue, right? So it's enqueue and then dequeue into an empty queue. That's adding a cycle latency. With the flow parameter, we put a bypass internal to the queue. In other words, if the queue is empty, I can, and the consumer is ready to receive. So both, there's one situation both producer is valid, consumer is ready. It'll actually bypass the queue's stateful bits and just pass the data straight through. So once again, you can imagine that this is an optimization. It can help reduce cycle count for some designs. However, at the same time, lengthens a potential critical path, right? You have data not going through registers here, but now going straight through. So these are just two knobs that exist. Okay, let's see the queue and play around with it. So to do that, we're going to make this chisel module wrapping around the queue. The module's not going to do anything too intelligent. It's just a way for us to instantiate this queue from standard library in a way to actually do some things we want to do with it. So what are we going to do? Well, we are going to, as you can see, for example, these pipe and flow parameters, we're going to pass these through from the outside. Initially, they'll both be false, so don't worry about that. But what does our, little dummy module do? It's going to have a counter, as the name suggests, counting into the queue, right? So this counter is going to have its count, and that's going to go into the enqueue port of the queue. And then for debugging purposes, we're going to have a way to expose that count from the counter, so you attach that to the output. But really, we expect whoever's using this module to be looking at the output port of the queue, and that's set up there. And so you may remember from before, we covered this notion with bundles of a bolt connection, right? So doing this little funny operator, this now connects up all three wires, right? There's the dot bits, dot ready, dot valid, boom, all at once, right? So once again, using some productivity advantages, not a lot of lines there. On the enqueue side, yeah, we're taking the bits from the count. In terms of going into the count, we are going to use the enable coming from the outside. So this entire module is going to have an external enable. Notice, however, for the counter, we're going to actually have some back pressure, right? So we're actually not going to count every time. We're going to count both when the enable coming into this module is true and the output of the counter, which in this case is going into the enqueue port of a queue, is ready to receive, right? And so when you have ready and valid both true, that's a dot fire condition. So even though it looks like a function call, you can think of dot fire as like being syntactically replaced by, io.enqueue.ready and io.enqueue.valid, right? It's kind of just like a shorthand for that. So if I was, for example, to print the Verilog, we're going to see a lot of stuff. We're seeing a lot of stuff because Chisel, the way it implements queues, uses a memory. That's what this memory is. But yeah, it's all packed in there. And you can see how, wait a second, pretty concise Chisel produced a lot of lines of Verilog, right? You're starting to see some of the benefit of what we're doing. Now, maybe a human wouldn't quite write the Verilog exactly this way, granted, but still, right? This line, for example, is taking three wires at once. These lines are, this is declaring three wires at once. This queue, which we're reusing, has a lot of components in there. It's kind of coming together. And yeah, this queue, as I said before, it has six freaking ports on it, and yet we only have a total of four lines connecting its IOs. Cool. So let's go ahead and play with some test bench. So uh, this test bench has multiple phases, and so we're going to kind of be dancing through this example. So what are we going to do? Well, we have our queue, we instantiate it, sure. What are these numbers here? Let's go remind ourselves. The first one is the maximum value of the counter. The second one is the number of entries in the queue. Okay. Uh, what are we going to do? Well, you can see that what we're going to do initially is fill up the queue, drain the queue, and then simultaneously NQ and DQ. So what do we mean by fill up the queue? That means we're going to be producing things, i.e. NQing, and by filling up, that means the capacity is decreasing because the queue is not draining, right? So you can see it kind of coming together, right? We're going to set the enable true for this entire module, which is going to give it the opportunity to count if it's possible. However, on the DQ side, on io.out, we're going to say we're not ready to receive, right? So that's why it's going to be counting into the queue. So we go ahead and run that real quick. I'll come out the rest for now. We're going to see that, right? That the count, which we are printing for debug reasons, like I said, this is a long print scheme I set up, kind of having all the fields we want in there. But yeah, so the count itself, you know, 0, 1, 2, 3. Look at the output of the module. I would pay less attention to the 0 and more attention to the fact that the valid bit. So the last thing V is the valid bit for the output. We see initially the queue is empty, so there's nothing valid coming out of it, so valid is 0. However, after you put a 0 into the queue, there now is something there, so it now is valid. And it happens at the value 0, and because we aren't advancing anything in the queue, it still is the value 0. Okay, now the second phase. We are going to drain the queue, meaning we're going to stop counting, so we turn enable to false. But now we're going to enable the queue to empty by, on the DQ side, the output side, saying ready is true. So if we let that run, so you can kind of have these little letters that kind of give you hints, right? Filling phase, draining phase. The count's no longer changing because we turn off that enable. We see on the output side, the valid is true and it gets a 0. Great. Valid is true and it gets a 1. Great. Valid is true, gets a 2. Great. Then all of a sudden, the queue is empty, right? The valid is false. So the fact that it's 0 doesn't matter so much as the fact that it's valid, it's false, right? So even though I don't talk a lot about don't cares in this course, with this ready valid signaling, right? If something is not valid, you shouldn't be looking at that data, right? It should be considered garbage. But let's kind of appreciate what happened here, right? Wait a second. I filled for 4 cycles and then I drained, but I only got elements 3 of those cycles? Yes, because the queue only has capacity of 3, right? So the queue filled up, and then that fourth element didn't get pushed on. Let's say I made the queue 1 bigger, then we can see we get things all 4 cycles, right? Or make this even smaller, make this more apparent. Same thing, right? You see, oh yeah, I even had all these signals kind of putting things in there, it only kind of comes through at that one point. Okay, now for the final situation, we're going to have a scenario of simultaneously NQing and DQing to this queue, right? So how are we going to set it up? Well, from before, the output is ready, and now we're going to turn the input enable also on to true. So we're both NQing and DQing the counters, putting things in the queue, we're taking things off the queue. Remember, this queue was drained at the end of this draining phase. So what's going to happen? Well, because it was drained, that first cycle is nothing to DQ because there's nothing valid in there. However, in that first cycle, because we're both simultaneously NQing and attempting to DQ, the next cycle, there will be something to drain, right? Um, and you can see it kind of wraps around. and it kind of goes through. So now we're kind of once again off and running. So once we have this situation of having, empty queue goes from 0 to 1 elements in the queue, and now there's always one element, we're kind of enqueuing and dequeuing. So still one element we're kind of going through. So I can show some more examples where I kind of treat some of these parameters, but I want to pause here for any questions so far. Let's tweak these parameters a little bit. So remember that notion we talked about this pipeline thing. Sorry, let's do flow first, right? So flow is not going to change the earlier stuff because the queue is either filling or draining, right? However, in a scenario at the end where the queue is empty and I'm kind of passing things straight through, so you can see down here, that queue is empty. I have to enqueue something and actually write it in there for a cycle before I can use it. With flow set to true, now all of a sudden I can grab it right away, right? Because I'm bypassing the queue. Cool. Now, type is a little bit more subtle, and maybe it's better demonstrated uh, down here, right? So, okay, so in the case of the simultaneous NQ DQ, let's go ahead and comment this out. So now we have a full queue, and I try to do simultaneous NQ DQ. Um, we have to kind of get ahead, right? In other words, uh, it may not be visible, but we actually are basically have. Oops, I commented out too much. That's why it's not working. We have to basically we have a scenario where basically you see just kind of a hitch in the output, right? So where's my hitch? This needs to run a little bit longer. Well, okay, here I am trying to break this, and we have a too robust of a synchronous system, and because it's decoupled, everybody's not losing any data. So look at the output signals going through here. I'm looking at when valid is true. What is the output value, assuming it's firing? It actually only fires in the simultaneous phase. You see, yeah, 0, 1, 2, 3, 0, 1. Yeah, so we actually didn't lose any counts, which is correct. The system's working as intended. But at this point, it may not be obvious. We have a queue where it's only using two of the three. Oh, that's why. No, never mind. That's with only using two of the three elements, right? Let's go back. Max files first. Yeah. If we could shrink this a little bit more, we can start seeing some of the consequences go down like a one element queue. So now you can see all of a sudden for one element queue, I have to, um, originally come through and then, sure, I have elements in there. I can pop that off, no problem. Then it's empty. With pipe, I can now push in there at the same time. So this is not what I'm describing. So yeah, you can imagine for a lot of queues, you probably want to turn pipe on to true. Flow, if you're sure it's on the critical path, maybe that on too as well. But these are just parameters. And when we come to this how to build a queue in a few lectures, you'll see that adding these knobs really nice, and this makes this queue much more robust, right? Because depending on scenario, you may or may not want this. The generator can do that for you, kind of encapsulating the generator. Question. How does flow affect the critical path? Great question. So to go back to our design here, flow allows for data to bypass the internals of the queue and basically kind of go straight from the producer to the consumer without going right through here. So if you had registers in here, or in this case, maybe a mem holding the data for the queue, you can imagine a critical path might be from the producer to into the queue or from the queue into the consumer. So like basically like half of this, right? If I have flow is true and I bypass that register in there, there's now a combinational path from the producer to the consumer. It typically goes through the queue module, but it's bypassing the state elements in there, right? So as a result, that could be a longer path. It's not guaranteed to be a critical path, but it could be. Cool. Other questions? Great. So that was, yes, go ahead. Oh, yeah, good question. So if I turn pipe on, how does that change the Verilog code? So let's dive into this, right? So you actually notice that Q is a module, it's instantiated. So unlike counter, which was a object, the Q in the Chisel standard library is actually a module. So when we instantiate it, we actually need to use this module wrapper around it. That's the way you instantiate a module. And if you forget which is which, That's part of why I pulled up the documentation on this. You can see the example where, yeah, they wrap it in modules. That way you know it has to be used as a module. Um, but yeah, so to the point, uh, so how is the queue implemented? The queue is its own module, right? Internally uses mems, but kind of the key thing is, you know, when they're able to do NQs or DQs, it actually has this logic internally, which we're kind of previewing a future lecture talking about this right now. Let's see what we can do. So you can see when it's able to do an NQ, it's when the NQ is both ready and valid. It's ready to do a DQ when both ready and valid. So right now with pipe false, um, it is making some decisions based on that. So uh, you can see if you go kind of trace through, I wish I had a search, but um, yeah. No, this is fun. Like I'm trying to dive through this. See, it's kind of confusing, right? But yes. Meanwhile, if I set this to true, it's going to change a little bit of that logic in there. Uh, yeah, it's going to go in there and change some of that logic involving, I think it's here maybe. Yeah, you can see NQ ready is not just if it's empty or if the DQ is also ready, right? Because that way it's kind of pulling through with the pipe. Good question. Other questions? Okay.